everyone, welcome to the course of Real-Time Embedded System. Today we will continue chapter number 6, that is of interfacing, and in today's lecture we are going to talk about advanced communication principles. As in our previous lecture, we discussed basic methods of interfacing. Those interfacing methods could be applied to interconnect components with an IC via on-chip buses or to interconnect ICs via on-board buses. In the rest of the slides, we will study more advanced interfacing concept and look at communication from more abstract point of view. In particular, we will study serial, parallel, and wireless communication. We also describe some advanced concepts such as underlaying, such as layering, and error detection, which are part of many communication protocols. Furthermore, we will highlight some of the popular serial, parallel, and wireless communication protocols used today. So let's start it. So in this slide, we will talk about advanced communication principle. So first of all, let's talk about layering. Layering is the concept to break complexity of communication protocol into pieces so that it is easier to design and understand. Lower level provides services to higher levels. Lower level might work with bits, while higher level works with packets of data. The lowest level in layering is physical layer. It's a medium to carry data from one point to another point or from one actor to another node. There are three most widely used communication that are parallel communication, serial communication, and wireless communication. In parallel communication, physical layer is capable of transporting multiple bits of data, whereas in serial communication, physical layer transports one bit of data at a time. And lastly, wireless communication, no physical connection needed for transport at physical layer. So we do not require any physical connection. And communication can take place over a number of different types of media, as you might know that, such as single wire, a set of wire, or radio waves. And we can also communicate via infrared. And we refer to the medium that is used to carry data from one device to another device. As I already told you, it's physical layer. Depending on the protocol, we may refer to an actor as a device or node. In either case, a device is simply a processor that uses the physical layer to send or receive data to and from another device. So in this section, we will talk about serial communication, parallel communication, and wireless communication. In addition, we describe communication principles such as layering, error detection, error correction, data security, and plug and play. So let's move on to next slide. So in parallel communication, we have multiple data, control, and possible power wires, and we send one bit per wire. High data throughput because of multiple wires with short distances. So because we are having multiple wires, we use this type of communication for short distances. However, it will provide the benefit of high throughput. Typically used when connected devices on same IC or same circuit board. Bus must be kept short, as we know that bus must be kept short, so we use this kind of communication from IC to IC, IC to same circuit board. Long parallel wire result in high capacitance values, which requires more time to discharge and charge. Data misalignment between wires increases as length increases. The disadvantages is higher cost and bulky. Along with this, there is a capacitance issue between the parallel wires. Also, there is an issue of data misalignment between the wires. So, parallel communication takes place when the physical layer is capable of carrying multiple bits of data. okay, from one device to another device. So these multiple bits, as I've already told you, could be control, power lines. This means that data bus is composed of multiple data wires, in addition to control and possibly power wires, running in parallel from one device to another. Each wire carries one of the bits. Parallel communication has the disadvantage of high data throughput. So it has the advantage of high throughput. If the length of bus is short, the length of parallel bus must be kept short, because long parallel wires will result in high capacitance values, and transmitting a bit on bus with higher capacitance value will require more time to charge and discharge. In addition, small variation in the length of individual wires of parallel bus can cause the received bit of data wire to arrive at different times. Such misalignment of data becomes more of a problem as the length of parallel bus increases. Another problem with parallel buses is the fact that they are more costly to construct, as I've told you, and this will make them bulky, especially when considering the insulation that must be used to prevent the noise from each wire from interfacing with the other wires. For example, a 32-bit wire cable connecting two devices together will cost much more and be larger than a two-wire cable. In general, parallel communication is used when connecting devices that reside on the same IC or devices that reside on the same circuit board. Since the length of such buses is short, the capacitance load, data misalignment, and cost problem, as I told you earlier, do not play an important role. So let's move on to next slide. So in this slide we are going to talk about serial communication. So we just have single data wire, which can possibly be control or and power wires, were transmitted one bit at a time. Higher data throughput with long distances. So if you have long distances, we can take advantage of higher data throughput. Less average capacitance, so more bits per unit of time. Cheaper, less bulky. Moreover, the thing is that it requires complex interfacing logic and communication protocol. Sender needs to decompose word into bits. Receiver needs to recompose bits into word. Control signal often sent on same wire as data, increasing protocol complexity. So, serial communication involves physical layer that carries one bit of data at a time. This means that data bus is composed of single data wire, along with control and possibly power wires, running from one device to another. In serial communication, a word of data is transmitted one bit at a time. Serial buses are capable of higher throughputs than parallel buses when used to connect two physically distant devices. The reason for this is that a serial bus will have less average capacitance, enabling it to send more bits per unit time. In addition, a serial bus cable is cheaper to build because it has fewer wires. This disadvantage of a serial bus is that the interfacing logic and communication protocol will be more complex. On the sending side, the transmitter must decompose data word into bits, and on receiving side, this receiver must compose bits into words. Most serial bus protocol eliminate the need of extra control signals, such as read and write signal, by using the same wire that carries data for this purpose. This is performed as follows. When data is sent, the sender first retransmits a bit called start bit. A start bit merely signals the receiver to wake up and start receiving data. The start bit is then followed by n bits of data. So initially we send a start bit and the start bit wake up the receiver, and then we send n bits of data, where n is the size of the word, and a stop bit. The stop bit signals to receiver the end of transmission. Often both the transmitter and the receiver agree on the transmission speed used to send and receive data. After sending a start bit, the transmitter sends all n bits at the predetermined transmission speed. Likewise, on seeing a start bit, a receiver simply starts sampling the data at a predetermined frequency until all bits are assembled. Another common synchronization technique is to use an additional wire for clocking purposes. Here the transmitter and receiver devices use this clock line to determine when to send or sample the data. So we do not need any extra control signal such as read and write signals by using the same wire that carries data for this purpose. So we do not require any read and write extra control signal. So let's move on to next slide. In this slide we are going to talk about wireless communication. Wireless communication eliminates the need of devices to be physically connected in order to communicate. So the physical layer used in wireless communication is typically either an infrared channel or radio frequency channel. Now infrared is an electronic wave frequencies just below visible light spectrum. Diode emits infrared light to generate signal. Infrared transistor detects signal, conducts when exposed to infrared light. It is cheaper to build, need line of sight, so it has limited range. So as I've told you, infrared uses electromagnetic wave frequencies that are just below the visible light spectrum, thus undetectable by human eye. These waves can be generated by using an infrared diode and detected by using an infrared transistor. An infrared diode is similar to a red or green diode, except it emits infrared light. An infrared transistor is a transistor that conducts, means that it allows current to flow from its source to drain when exposed to infrared light. A simple transmitter can send ones by turning on its infrared diode, and can send zeros by turning off its infrared diode. Correspondingly, a receiver will detect ones when current flows through its infrared transistor and zeros otherwise. Now the advantage of using infrared communication is that it is relatively cheap to build transmitters and receivers. The disadvantage of using infrared is that it needs line of sight between the transmitter and receiver, resulting in a very restricted communication range. The other wireless communication method is radio frequency. Radio frequency basically fall in electromagnetic wave spectrum. Analog circuitry and antenna needed on both sides of transmission, that is on receiving and as well as on transmitting. Line of sight not needed, transmitted power determined range. So radio frequency uses electromagnetic wave frequencies which fall in radio spectrum. A transmitter here will need to use analog circuitry, so we need to use analog circuitry here, and an antenna to transmit data. Likewise, a receiver will need to use an antenna and analog circuitry to receive data. One advantage of RF is that generally a line of sight is not necessary and thus longer distance communication is possible. The range of communication is of course dependent on the transmission power used by the transmitter. So that was about the wireless communication. Let's move on to the next slide. Before I start error detection and correction, there are a few points about the previous slide. RF transmitters and receiver must agree on specific frequency in order to send and receive. Using frequency hopping, it is possible for the transmitter and receiver to communicate while constantly changing the transmission frequency. Of course, both devices must have a common understanding of the sequence of frequency hops. Frequency hopping allows more devices to share fixed set of frequencies and is commonly used in wireless communication protocol designed for network of computers and other electronic devices. So in error detection correction, often part of bus protocol. So this error correction and detection is a part of bus protocol. Error detection has the ability of receiver to detect errors during transmission, whereas error correction is the ability of receiver and transmitter to cooperate to correct problems, typically done by acknowledgement and retransmission protocol. So bit error means that a single bit is inverted. Burst or bit error means consecutive bits received incorrectly. And for parity is known as extra bit sent with word used for error detection. So we have three types of parodies here. Parity here, odd parity, even parity. So in odd parity, data word plus parity bits contains odd number of ones, whereas in even parity, data word plus parity bit contains even number of ones. So if you have even parity, we will have even number of ones. If we have odd parity, it means that we have odd number of ones. Always detect single bit error, but not all burst bit errors. So by using parity bit, we can only detect bit errors, but not all burst bit errors. There is another thing used in error detection and correction, that is checksum. Extra words sent with packet data of multiple words. So if we have multiple words, we will send extra data of packet. And what we will do, extra word contains X or sum of all data words in packet. So we will send checksum. Checksum is just like extra word with data packet of multiple words. So we will send a kind of a copy of the original data, and at the receiving we will do XOR. So if we have different data packets, we will have 0. If we will have same data packets, for same data packets we will have 0, and for different data packets we will have 1. So let me recap this slide for you. Error detection is the ability of receiver to detect errors that may occur during the transmission of data, word or packet. The most common type of errors are bit errors and burst of bit errors. A bit error occurs when a single bit in a word or data packet is received as inverted. A burst of bit error occurs when consecutive bits of words or data packets are received incorrectly. Given that an error is detected, error correction is the ability of a receiver and transmitter to cooperate in order to correct the problem. The ability to detect and correct error is often part of bus protocol. And we will discuss next parity and checksum error detection algorithms, which are commonly used in bus protocol. Parity is a single bit of information that is sent along with a word of data by the transmitter to give receiver some additional knowledge about the data word. This additional knowledge is used by the receiver to detect some degree a bit or burst of bit error in receiving a word. Common type of parity are even or odd. Odd parity is a bit that, if set, indicates to the receiver that data word bits plus parity bit contain an odd number of ones. Even bit is a bit that, if set, indicates to the receiver that data word bits plus parity bit contains an even number of ones. And prior to sending a word of data, the transmitter will communicate the parity and send that along with the data word to the receiver. On reception of the data word and parity bit, the receiver will compute the parity of data and make sure that it agrees with parity bit received from the transmitter. If a parity bit check fails, it indicates the certainty that there was at least one transmission error. Parity checks will always detect a single bit error. However, burst bit error may or may be detected by parity checking an even number of errors, for example. Now we talked about checksum. Checksum is a strong form of error checking that is applied to a packet of data. A packet of data will contain multiple words of data. Using parity checking, we use one extra bit per word to help detect errors. Using checksum, we use extra word per packet for the same purpose. For example, we may compute XOR sum of all the words in the packet and send this value along with the data packet. So what we did, we computed the XOR sum of all data words in a packet and we send it this along with the data packet. Upon receiving of the data packet words and the checksum word, the receiver will compute the XOR sum of all the data words it received. If the computed checksum word equal to the received checksum word, the data packet is assumed to be corrected. Otherwise, it is assumed to be incorrect. Again, not all error combination can be detected. We can of course use both parity and checksum for stronger error checking. And there is an example in your book. Please go through that example regarding the error detection and correction. So in parity, it's just a weak form of error detection, whereas checksum is a stronger form of error checking. Okay, so we take the XOR of all the data words and we send that checksum, and at the receiver side we compute the XOR sum of all the data words it received, and then we compare our checksum with the received checksum to make sure that there are no errors. Let's move on to the next slide. So now we'll talk about the serial protocol. There are basically four serial protocols that are widely used. Number one is I2C protocol, the CAN protocol, the FireWire protocol, and the USB protocol. The I2C is also known as Inter-IC protocol. It's a two-wire serial bus protocol developed by Philips Semiconductors almost 20 years ago. This protocol enables peripheral IC to communicate using simple communication hardware. Data transfer rates up to 100 kilobits per second and a 7-bit addressing possible in normal mode, 3.4 megabits per second and 10 bits addressing in faster mode. So it basically has multiple modes. In one mode it transmits at 100 kilobits per second, and other modes it transmits at 3.4 megabits per second. Common devices capable of interfacing I to C. So where we use this kind of a protocol, for communication: EPROMs, flash, and some RAM memory, real-time clocks, watchdog timers, and microcontrollers. So I2C protocols used in communication, serial communication in these devices: EPROMs, flash, some RAM memory, real-time clock, watchdog timers, and microcontrollers. Let's move on to next slide. So this slide basically shows a simple I2C network. The bus consists of two wires, a data wire called serial data line and a clock wire called serial clock line. The I2C specification does not limit the length of bus wire as long as total capacitance of the bus remain under 400 picofarad. In this example, there are four devices attached to bus. One of these devices, the microcontroller, is the master. The other three devices, a temperature sensor, EEPROM, and a LCD controller, are servants. Each of these servants is assigned unique address, as you can see in figure. Address for EEPROM is 0x01, address for So in this slide we will talk about the serial communication protocol, that is CAN. CAN stands for Controller Aerial Network, and this protocol is used for real-time applications. It is the protocol that was developed by Robert Bosch, and it was originally designed for communication among the components of car. Now applications are growing, and it includes elevator controller, photocopiers, telescope, production line control system, and medical instrumentation. It has data rate up to 1 megabits per second and 11 bit of addressing. Common devices interfacing with CAN is 8051, compatible 8592 processor, and standalone CAN controller. So we can interface 8051 with this processor and standalone CAN controllers. Now the actual design of CAN bus not specified in protocol requires devices to transmit/detect dominant and recessive signals to and from bus. For example, 1 is equal to dominant and 0 is equal to recessive if single data wire used. Bus guarantees dominant signal prevails over recessive signal if asserted simultaneously. So there is a dominancy of 1 over 0. So the CAN's specification does not specify the actual layout and structure of the physical bus itself. Instead, it requires that a device connected to CAN bus is able to transmit or detect on the physical bus one of two signals called dominant or recessive. For example, as I've already told you, dominant signal may be represented by logic 0 and recessive by logic 1 on a single data wire. Furthermore, the physical CAN bus must agree that if one of the two devices assert dominant signal and other devices simultaneously a recessive signal, the dominant signal prevails. So in the end, I want to conclude, if some device asserts recessive signal and some device asserts dominant signal, so the priority will be given to the dominant one. Okay, so that was about the serial protocol of CAN. Let's move on to next slide. Another form of serial protocol is FireWire protocol. FireWire protocol, also known as iLink, links and it is IEEE 1394. Higher performance serial bus developed by Apple Computer, designed for interfacing independent electronic devices, for example desktop, scanner, and data transfer rates up to 12.5 to 400 megabits per second, and it has 4-bit addressing. It has plug-and-play capabilities, packet-based layered design structure. Applications using FireWire includes disk drive, printer, scanner, cameras, capable of supporting a LAN similar to Ethernet. So this protocol can also support LAN. 64-bit addresses, 10 bits for network IDs, 10234 subnetworks, 6-bit for node IDs. Each subnet have 63 nodes, 48 bits for memory address. Each node has 281 terabyte of distinct location. So we have like 64 total address bit, out of which 10 are used for network ID, 6 are used for node ID, and 48 are used for memory addresses. And from 10 bits of network ID we can make 1023 subnetworks, so 2 raised power 10. And for 6 bits of node ID, each subnet can have 63 nodes, so 2 raised power 6. And from 48 bit of memory address, each node can have 281 terabytes of distinct location. So that is quite a high powerful serial protocol, that is FireWire, and it is being developed by the Apple, and it is used to interface independent electronic components. Let's move on to the next slide. So finally we have the USB protocol, and you know that USB is a serial communication, and it stands for Universal Serial Bus. Easier connection between PC and monitors, printers, digital speakers, modems, scanners, digital camera, joystick, multimedia, game equipment, you name it, and you will have a USB connection interfacing with it. It has two data rates. One is 12 megabits for increased bandwidth of devices. Other is 1.5 for low speed devices, for example game, joysticks, game pads. So tiered star topology can be used. It means one bus device connected to PC. So we just connect one USB to PC. Hub can be embedded in devices like monitors, printer, or keyboard, or can be standalone. Multiple USB devices can be connected to hub. Up to 127 devices can be connected like this. So it has tiered star topology. So in tiered star topology, one USB device connected to PC. So this USB acts as a hub, and we connect multiple devices to that hubs, and we can connect up to 128 or 127 USB devices to this hub. Now USB host controller. USB host controller manages and controls bandwidth and driver software required by each peripheral. It dynamically allocates power downstream according to devices connected or disconnected. So it manages the power, and it manages the control bandwidth, and it provides the software for the peripherals. So that was about the serial protocol. Now, like the way we talked about the serial protocol, we started with the I2C protocol, then we talked about the USB protocol, we also talked about the FireWire protocol, and we also talked about the CAN protocol. Like the way we have two most popular protocol in parallel communication. Number one is PCI protocol, and the number two is ARM bus protocol. So we'll start with the PCI bus protocol. PCI bus protocol stands for Peripheral Component Interconnect. It is high performance but originated at Intel in early 1990s. So it's a high performance bus originated at Intel in early 1990s. And it is a standard adopted by industry and administered by PCI SIG. So PCI SIG stands for Peripheral Component Interconnect Specialist Interest Group. So that's a special interest group in PCR. So we use parallel protocol PCI bus to interconnect chips, expansion board, processor memory. As I've told you that we use parallel communication for short distance for IC to IC, IC to chip. So we do not use parallel protocol or parallel communication for long distances. So it interconnects chips, expansion board, processor memory, bus system, subsystems. It has a data transfer rate, quite a high data transfer rate of 127 to 508 megabits per seconds, and a 32-bit addressing, which can be extended to 64-bit while maintaining the compatibility with 32-bit schemes. It has a synchronous bus architecture and multiplex data address lines. So that was about the PCI bus, which is the protocol of parallel communication. Let's move on to next slide. Another type of parallel protocol is ARM bus. ARM bus stands from Advanced Risk Machine Bus, designed and used internally by ARM Corporation. Interfaces with ARM line of processor. So this protocol only works with ARM line of processor. Many IC design companies have own bus protocol. So most of the IC design companies have own bus protocol. For example, ARM is used for ARM line of processor. Data transfer rate is a function of clock speed. So if clock speed of bus is x, data transfer rate means 16 into x bits per second. It has 32 bit of addressing. Let's move on to next slide. So in this slide we will talk about the wireless protocols. So wireless protocols, we have three emerging wireless protocols, namely IrDA, Bluetooth, and IEEE 802.11. So IrD protocol suit that support short-range point-to-point infrared data transmission. This protocol was created and promoted by Infrared Data Association IrDA. It has data transfer rate of 9.6 kilobits per second to 4 megabits per second. IrD hardware deployed in notebook computers, printers, PDAs, digital cameras, public phones, cell phones. So it is the same infrared that is used in our cell phones. So lack of suitable drivers has slowed the use of applications. So for using this kind of a protocol we need specific drivers, and because of the lack of drivers we are not using infrared very often. Windows 2098 now include the support of drivers of infrared, and it is becoming popular in embedded system. Let's move on to next slide. Another type of wireless protocol is Bluetooth protocol. Bluetooth is a new and global standard for wireless connectivity. This protocol is based on low-cost short-range radio link. The radio frequency used by Bluetooth is globally available. When two Bluetooth-equipped devices come within 10 meters of each other, they can establish a connection. Because Bluetooth uses radio-based link, it does not require line-of-sight connection in order to communicate. For example, your laptop could send information to a printer in next room, or your microwave oven could send a message to your cordless phone telling you that your meal is ready. In the future, Bluetooth is likely to be standard in tens of millions of mobile phones, PC, laptops, and whole range of electronic devices. Let's move on to next slide. In this slide we will talk about the final wireless protocol, that is IEEE 802, that was proposed by the IEEE for wireless local area networks. It is just the same protocol that we use in our daily life for Wi-Fi. It specifies parameters for physical and media access layer, MAC layer. The parameter it specifies for physical layers are physical layer, handles transmission of data between nodes. It offers data rate of 1 or 2 megabits per second. It operates within the frequency range 2.4 GHz to 2.4835 GHz, that is an RF band, or it also works in infrared range, that is from 300 to 42800 GHz. And the MAC layer stands for Media Access Control Layer, and this is responsible for maintaining order in shared medium. So MAC layer is responsible for maintaining the order in the shared medium and avoidance of collision avoidance and detection. So it works to avoid data collision and detection of errors. There are two different ways to configure network. There is ad hoc and infrastructure. In ad hoc network, computers are brought together to form a network on fly. Here there is no structure to the network, there is no fixed point, and usually every node is capable to communicate with every other node. And although it seems that order would be difficult to maintain in this type of network, special algorithms have been designed to elect one machine as the master of the network while the other being the servants. Although algorithm is ad hoc network, another algorithm in ad hoc network architecture uses broadcast and flooding method to all other nodes to establish whos. The second type of network structure used in wireless LAN is the infrastructure. The architecture uses fixed network access point with which mobile nodes can communicate. So either you have like open network, which is known as ad hoc network, in which everybody can send and receive messages and we do not have like any control, so we cannot maintain the order. The second type of architecture is infrastructure, in which we have fixed network access points, like the way we have routers with which we can connect. These network access points are sometimes connected to landlines to widen the LAN capabilities by bridging wireless node to other wired node. If service area overlap, handoffs can occur. So if handoffs mean that if, for example, you go from one point to another point and you have the same Wi-Fi, so a time will come when you will have a disconnection because your cell phone or your system will be handoffing from one access point to another access point. So anyways, this was the protocol being proposed by IEEE, and this is used to specify two parameters, that is physical and MAC layer. So let's move on to next slide. So in this chapter we'll talk about the basic protocol concept. We'll talk about the actor, direction, time multiplexing, control methods. We talked about the general purpose processor interfacing, that is port based, bus based. We talked about IO addressing, that is memory mapped IO, standard IO. We talked about interrupt handling, in which we talked about fixed or vector based interrupt, or we also talked about the compromise between fixed and vector, that is vector table. We also talked about memory, direct memory access. We talked about arbitration. We talked about parity arbiter. We talked about daisy chain arbiter. We also talk about the bus hierarchy, and then finally we talked about the advanced communication protocols, in which we talked about parallel protocols, we talked about serial protocols, and we also talked about wireless protocols, that was infrared data association, Bluetooth, and IEEE 8021. So that was about the interfacing chapter. So from next time we will start our software portion, because so far what we have studied comes under hardware portion. As I've told you that embedded system designer must need to understand both both the software portion and the hardware portion. So we are currently done with the hardware portion for now, and we will look into the software portion for next lecture. Thank you very much.